You are probably burning thousands of dollars in GPU compute right this second, just like running RLVR to get your model to reason better.
Oh, absolutely. It's incredibly expensive.
Right, but what if you're just navigating through optimization noise? Like, what if the final answer could literally just be found with a simple straight line? Welcome to AI paper slop. Today we are looking at you only need minimal RLVR training, extrapolating LLMs via Rank-1 trajectories by researchers at the University of Virginia and Washington University in St. Louis. And here is the core insight right up front.
Yeah, so if you're training large language models right now, reinforcement learning with verifiable rewards, or RLVR, using algorithms like GRPO, that is pretty much the current gold standard.
Right, especially for things like math and logic where there's a strict right or wrong answer.
Exactly. But the bottleneck is it's severe. It requires hundreds of optimization steps. We were talking about days of continuous compute on, massive clusters.
Which hurts the wallet.
Yeah, big time. But these researchers actually analyzed the weight updates during this process, and they found something completely counterintuitive.
Yeah.
The updates are shockingly simple. They exist in an extremely low rank space, specifically rank 1, and they evolve almost perfectly linearly over time.
Which is wild. And that leads directly to their proposed solution, which they call RELX. Basically, by observing just the first, say, 15 to 20% of the training run, you can use singular value decomposition to isolate that rank 1 trajectory.
Right.
And then you just extrapolate it with a basic linear regression. You can predict the final model weights with literally zero additional training costs.
Zero. It's amazing.
And the extrapolated model actually matches or even beats the fully trained RLVR model. So, okay, that is a TLDR. But to actually understand why this works, we really need to unpack the underlying geometry of the weight space during RLVR, because this challenges fundamentally held assumptions about how these models learn to reason.
It really does. So let's contextualize what a standard RLVR pipeline actually looks like under the hood.
Yeah, let's lay the groundwork.
So you're likely using GRPO. You generate multiple completions, score them against a deterministic verifier, like, checking if the final math answer is perfectly correct, and then you update the policy.
Right.
The assumption in ML, like the standard mental model we all have, is that your model is navigating this highly non-convex, incredibly high-dimensional loss landscape.
Yeah, like you're shifting billions of parameters, you're trying to dodge local minima, you're dealing with all this highly variable gradient signal.
Exactly. We basically assume that developing complex reasoning capabilities requires this chaotic, winding path through the weight space.
If the parameter space is like a densely populated, chaotic city, we assume RLVR is navigating this incredibly complex maze of streets.
Right. That's a perfect analogy. But the researchers decided to actually test this. They looked at the parameter deltas.
So just the difference between the base model weights that is 0 and the checkpoint weights at step T.
Yes. And when you flatten those deltas and apply singular value decomposition across the training steps, the math shows something entirely different than a winding maze.
What does it show?
Two very distinct empirical findings. The first is that RLVR updates are just intensely low rank.
Okay, how low are we talking?
Like rank 1 low. When you run that SVD on the parameter deltas, a single dominant direction, literally one rank 1 component per weight tensor, captures almost all of the task-relevant changes.
Oh, wow. So just one direction matters.
Yeah. If you reconstruct the checkpoint using only that single rank 1 component, and you just strip away everything else, it preserves nearly all the downstream performance gains on the math tasks.
I mean, that completely contradicts the whole maze assumption. Out of a parameter space of billions, the model functionally only cares about one specific direction per tensor to get better at math.
It's crazy. And then there's the second finding, which is the linearity.
Right, the straight highway part?
Exactly. If you project the weight updates onto that dominant singular vector, you derive a scalar sequence. Let's call that coefficient CT.
Okay, so CT represents how far the model has moved along that one vector at any given step.
Yes, exactly. And that coefficient grows almost perfectly linearly with the training steps.
Really? How linear are we talking?
Your R-squared value is greater than 0.98 for most tensors.
Wait, greater than 0.98? That is essentially a mathematically perfect line in the real world.
It really is.
So it's like instead of navigating a complex maze of city streets to find the reward, the model is just pouring concrete for a massive straight highway. and it's just driving down it at a constant speed.
Yeah, that's exactly what it's doing. It reduces this seemingly impenetrable high-dimensional optimization problem into a super predictable structured pattern.
That's mind-blowing. The temporal dynamics within that rank 1 subspace are just simple.
Right. The model isn't accelerating wildly or zigzagging around to find the reward. It's just moving forward.
So, okay, if we know the model is just moving in a straight line at a constant speed, we obviously don't need to simulate the entire drive.
No.
We can just calculate where it's going to end up. So let's get into the mechanics of how the RELEX algorithm, which stands for reinforcement learning extrapolation, how it actually executes this practically.
Sure. So it is a 3-step, entirely training-free algorithm. Well, training-free for the extrapolation part.
Right.
Step 1 requires a short prefix of the actual training run. They call this T-cut.
Yeah.
So, for example, you might run the first 75 steps out of a planned 500-step RLVR training run.
Okay, so the heavy compute, the actual RL part, is restricted entirely to that short initial window.
Yes. You just bite the bullet for the first 15%. Then for each parameter tensor, you compute the parameter deltas for those first 75 steps.
Right.
You flatten them, stack them into a trajectory matrix, and you use truncated SVD to extract the top right singular vector.
And that becomes your rank 1 dominant direction. We found the highway.
Exactly. You've got the direction.
So how do we determine the velocity? How fast it's driving?
That's step 2. You project the observed deltas from those first 75 steps onto this rank 1 direction. That gives you your sequence of scalar coefficients.
Okay, the CT values we talked about.
Right. Then you just fit a line to those points using ordinary least squares. Good old OLS.
Wait, just OLS.
Yeah, you are literally just finding the slope and intercept of that coefficient trajectory. Y equals mx plus b.
That is so funny. Instead of relying on some secondary meta network or a complex implicit mapping to predict the weights, they literally just use middle school math on the scalar coefficient.
It is almost absurdly cheap to compute. I mean, SVD takes a minute and OLS is basically instantaneous.
It bypasses the vast majority of the RL compute. Okay, so what's step 3?
Step 3 is the actual extrapolation. You take that linear equation and you plug in your target step, say step 500.
Right.
You calculate the predicted scalar coefficient for that specific step, multiply it by your rank 1 direction vector, and then you just add that predicted delta back to the base model weights.
And you do this for all the tensors?
Yep, across the board, and boom, you have your extrapolated model.
Okay, as an ML engineer, I have to introduce some heavy skepticism here.
I figured you would.
I mean, fitting a 2D line to an LLM's learning dynamics, it feels inherently flawed. Why assume the trajectory won't eventually accelerate or hit a hard plateau? Complex loss surfaces don't usually map to a simple linear equation.
Right.
Like, why didn't a more complex function work better to capture the nuances of the learning curve?
That is the exact question the ablation studies in this paper address. It's the most counterintuitive part. To understand why the absolute simplest function works best, we really need to look at the benchmark results and this concept of spectral denoising.
Okay, let's ground this in the data first. How did RELEX actually perform on state-of-the-art models? Because if it doesn't work, the math doesn't matter.
Fair point. So they evaluated RELX on 3 models: Qwen 2.5 Math 1.5b, Qwen 3 4b base, and Qwen 3 8b base. And they tested primarily on the math benchmark.
Which is standard for reasoning evils right now.
Exactly. And using only 15 to 20% of the training steps, our RELEX either matched or straight up beat the full 500-step RLVR models.
Oh, wow.
Yeah, so on the Qwen 2.5, 1.5b model, our RELEX achieves 71.6% accuracy compared to the full model's 71.5%.
Wait, it beat it by a fraction, but
Yeah.
still. But does it just, overfit to the immediate training distribution? Or does the extrapolated reasoning actually hold up on harder problems?
That's the best part. It actually improves generalization. They evaluated the models on heavily out-of-domain Olympiad-level benchmarks.
It's the really hard stuff.
Yeah, AME 25, AME 26, MT 25 Olympiad bench, and AMC 23.
Okay.
And RLX outperformed the full RLVR on average across all these data sets. The extrapolated model was actually more robust than the model that actually sat there and completed the full training run.
Okay, returning to my skepticism, how on earth can a linear fit outperform the actual RLVR algorithm? What happens if you try to capture more of the variance in the weight updates using rank 5 or rank 10 extrapolations? Wouldn't more information be better?
You would think so. But this is where the underlying mechanics of RLVR become super visible. When you look at the explained variance of the weight updates, component 1 that rank 1 vector holds about 81.4% of the total variance.
And its trajectory is smooth, like you said.
Remarkably smooth. But components 2 through 5, they are entirely different beasts. They are erratic, they fluctuate wildly, and they are completely nonlinear.
Oh, I see. So the stochastic sampling, like the random exploration the algorithm does to generate completions and check them against the verifier, that randomness is getting trapped in those lower singular values.
Precisely. That is the policy gradient variance. The RL algorithm is basically constantly jittering around the weight space, trying to optimize the reward.
Right.
So if you try to extrapolate using rank 5 or rank 10, performance actively drops because you are mathematically adding optimization noise back into your clean trajectory.
Which explains why the baseline weight extrapolation method fails so hard. Like if you just draw a line between two checkpoints in the raw weight space without using SVD.
Yeah, you are including all the garbage noise from components 2, 3, 4, and 5.
The paper explicitly shows that SVD projection acts as a spectral denoiser.
Exactly. It preserves the stable, task-relevant reasoning signals in the rank 1 component, and it completely filters out the stochastic optimization noise inherent to the RL process.
It's just a giant math filter. That makes so much sense. But, okay, what about the function fitting itself? Even if the trajectory is relatively smooth, surely a neural network or, I don't know, a polynomial regression could map it more accurately than a straight line.
The researchers tested that assumption super thoroughly because they probably thought the exact same thing. They tried fitting polynomials to the rank 1 trajectory instead of a linear fit. The polynomials completely collapsed. They suffered from extreme Runge's phenomenon.
Oh, where the polynomial just oscillates crazily at the edges.
Yes. Over-indexing on these tiny microfluctuations in the early training steps and then spiraling off into infinity when extrapolated out to step 500.
That's hilarious. So they tried neural networks too.
They did. They even tried training a 3-layer transformer to model the trajectory, assuming a neural net could capture some hidden temporal dynamic.
And let me guess, it didn't help.
It offered absolutely no consistent advantage over the simple OLS line. None. It just introduced computational overhead.
Wow.
The geometry of the rank 1 trajectory is genuinely, fundamentally linear. The complexity of those modeling tools was actively detrimental because there was literally no complex dynamic to capture.
It's just a straight line. I love that. But there is a counterintuitive finding here regarding the final matrices themselves.
Yeah, there is.
Because if RLX matches or beats the performance of the Step 500 model, the logical assumption is that the RLX weights must look nearly identical to the Step 500 RLVR weights. Like they end up in the exact same spot in the vector space.
Right, that would make sense, but they do not.
Okay, why not?
There is a phenomenon the paper calls weight space alignment drift. If you take the mathematically extrapolated weights at step 500 and compare them to the actual RLVR weights trained to step 500, they drift significantly away from each other.
By how much?
The directional similarity drops from 0.72 early in the training all the way down to 0.35 by step 500.
Wait, so they're pointing in totally different directions, and what about the magnitude?
The magnitude of the weights is also totally different. The magnitude ratio over-extrapolates to roughly 2.7.
So RLEX is predicting weights that are pointing in a somewhat different direction in the high-dimensional space and are nearly 3 times as large in magnitude as the actual model's weights.
Yes, and yet it yields better out-of-domain reasoning.
That is fascinating. So RLEX is not perfectly predicting the true RLVR weights. It's predicting a purer, highly exaggerated version of the weights. Because it completely lacks the optimization noise, it basically just scales up that pure reasoning vector to an extreme degree. Like the actual model gets bogged down by its own sampling noise and plateaus, but RLX just ignores the noise and keeps driving down the highway.
That's exactly it. It creates a purer instantiation of the reasoning capability than the actual RLVR algorithm can ever reach on its own. The RL process is constantly fighting the baggage of its own gradient variance. RELEX simply extracts the signal and cranks the volume.
Man, that is so cool. Let's ground this for deployment, though, because there's always a catch. What is the catch here? We can't just, arbitrarily hard-code a T-cut of 75 steps and expect it to work for every single architecture in the open source ecosystem. Right?
No, you definitely can't. The sensitivity to the T-cut observation window is the primary limitation that engineers need to manage here. It is highly, highly model-dependent.
Okay, break that down for me.
So the Quinn 2.5, 1.5b, and Quinn 3 8b-based models, they actually prefer longer observation windows. If you provide a T-cut of 125 steps, they extrapolate beautifully, And they remain stable even if you push the extrapolation all the way out to 1,000 steps, which is double the original training run.
But the Qwen 3.4b base model degrades if you use that exact same window.
Oh, terribly. It requires a much shorter prefix, like 75 steps. If you try to extrapolate the 4B model out to 1,000 steps using a 125-step window, the accuracy drops off a cliff, falling to around 50%.
Oh, wow. So the Rank-1 direction isn't equally stationary across all model architectures. In some models, that highway SVD finds stay straight forever. In others, the subspace might shift slightly after a certain number of steps, and your straight line extrapolation suddenly just shoots off into the wilderness.
That is the exact problem. So adaptive subspace selection is the absolutely necessary next step for deployment.
Right.
ML engineers will need to monitor the singular value drift online during the early training steps.
So you wait for the Rank-1 direction to stabilize.
Yep. Establish your t-cut dynamically based on that stability, compute your linear fit, and then extrapolate. You just have to empirically validate that stability window for your specific model family before you deploy this at scale.
Sure, it requires some tuning to find the optimal window, but the compute savings, going from days of RL down to a few hours, are so significant that it's entirely worth the engineering effort to dial it in.
Absolutely. The ROI is undeniable.
You know, as we wrap up this analysis, this research forces a much broader, almost philosophical question about post-training in general.
Yeah, it really does.
We constantly talk about reinforcement learning as a process of teaching the model how to reason step by step, like we're imparting new knowledge.
But if RLVR, which is, again, a highly stochastic, computationally expensive optimization process, if it is ultimately just isolating and scaling a simple, linear Rank-1 path through the weight space,
does that mean we aren't actually teaching the model anything new during post-training?
it really makes you wonder.
Right, like, are these reasoning capabilities just a pre-existing latent vector formed during pre-training? And RLVR is merely an incredibly inefficient way to turn up the volume on that specific vector while fighting its own static.
It strongly implies that.
And if that is true, why on earth are we spending millions of dollars on complex reinforcement learning algorithms when we could just be searching for these latent geometric directions directly in the base models?
It suggests the reasoning is already there. The future of alignment might not be reinforcement learning at all. It might literally just be geometry.
Well, that is a thought to keep you up at night. Thank you for joining us for this session of AI Paper Slop. Keep questioning the landscape, and we will see you next time.